Great morning, everyone. Today, I'm going to walk you through the basics of an amnesic automatic computer design. Imbalances in technology scaling have rendered the energy efficiency of computation, have improved actually the energy efficiency of computation more than the energy efficiency of data communication. The gap is unfortunately widening, and here we have an example. The energy of a 64-bit SRAM load normalized to the energy of a 64-bit fused multiply add. And the ratio is increasing from approximately 1.55 to almost 6x as we move from 40 nanometers to 10 nanometers. And the picture looks worse for the main memory communication. In this case, recomputing data can become more energy efficient than memorizing and retrieving pre-computed data. And in the following, I'm going to refer to this new mode of execution as amnesic, which opportunistically replaces the communication of a data value with local recomputation only if more energy efficient. If we constrain the communication at microscale to the communication between the processor logic and the main memory, this translates into replacing each energy-hungry load with a sequence of recomputing instructions. Such arithmetic logic instructions form a backward slice of execution, and I'm going to refer to this slide as a recomputing slice in the following. Now, the execution of arithmetic logic instructions to generate a data value, which would otherwise be loaded from memory, does not come for free. And the energy overhead of each replaced load sets, in fact, the energy budget for the recomputation along a recomputing slide. Therefore, amnesic execution is useless if the energy cost along a slide, if the energy cost of recomputation along a slice exceeds this budget. There are more opportunities. If we can eliminate all dynamic instances of a load and replace it with the corresponding recomputing slice, we can also eliminate all matching stores, and in this manner we can also reduce the memory footprint on top of the energy and latency of communication. Next, I'm going to stick to this microscopic scale for communication, so we will be talking about the communication between the processor logic and the main memory. And I will walk you through the basics of a proof-of-concept amnesic computer design. Particularly, I'm going to talk about 4 axes which span the design space, namely how to determine which data values to recompute, how to identify instructions to recompute data values, how to orchestrate recomputation at runtime, and how to protect architectural state during recomputation. Let us start with the first axis, how to determine which data values to recompute. Well, practically any data value where the energy cost of the corresponding load significantly exceeds the energy cost of recomputation along the respective data slice. The energy cost of the load is dictated by the level in the memory hierarchy where the target data value resides, or more specifically, the level in the memory hierarchy to service the load. The energy cost of recomputation, on the other hand, is dictated by the length and mix of the instructions within a recomputing slice. So to be able to answer this question, we need 2 accurate energy estimates. Before moving forward, let us take a closer look at a recomputing slice. It is an upside-down tree where each node forms or corresponds to an instruction. At the root, we have the producer instruction of the data value v, which is to be computed, then or recomputed. Then at level 1 reside the producer instructions of the input operands of the root, and so forth and so on until we hit the leaves. The leaves are terminal instructions. Their input operands may be read-only data, such as program inputs, so these input operands won't have any producers, or they may also be constants. But at the leaves, we can also have instructions where the recomputation of the producers of their input operands is not energy efficient. So for amnesic execution to work, we need to make the input operands of the leaves timely available and also energy efficiently. And the energy cost of recomputation along a recomputing slice should also include the energy cost of retrieving the input operands of the leaves. Once the input operands are provided, during recomputation, data flows from the leaves all the way down to the root. Coming back to the first question, how to determine which data values to recompute. In the proof of concept design that I'm going to cover today, we offload this task to the Amnesic Compiler. The problem here is the compiler can only probabilistically estimate at runtime where the respective data value would reside. But as I'm going to show you in the evaluation, this choice is still legitimate, just subject to the accuracy of the probabilistic energy model that the compiler uses. So the compiler needs two energy estimates to draw a decision, the energy of the loads, but at the same time the energy to recompute along a recomputing slice. So to estimate the energy of recomputation, the compiler has to track dependency change to construct the actual recomputing slices, and the instruction mix in each recomputing slice dictates the energy cost of recomputation. By doing this, the compiler also addresses the question of how to identify instructions to recompute data values. So practically, it keeps adding instructions across a dependency track to the recomputing slice as long as the anticipated cost remains significantly lower than the budget set by the cost of the respective load instruction. On top of that, the compiler, the Amnesic compiler, annotates code to demarcate recomputation boundaries. To this end, it uses ISA extensions, semantically similar to procedure call and return instructions at the entry and exit, respectively. Now, runtime orchestration of recomputation is the business of the Amnesic Scheduler. The Amnesic Scheduler has to decide whether and when to trigger recomputation by following Amnesic compiler hints about the potential recomputation targets and by tracking where in the memory hierarchy the load would actually be serviced. To this end, the Amnesic Scheduler can use different policies, such as a static policy, which ignores all sorts of runtime information, to trigger recomputation by blindly following Amnesic compiler hints. So any load which is identified by the Amnesic compiler as a potential candidate would be blindly replaced by the corresponding recomputing slice in this case. Alternatively, the scheduler can use dynamic policies such as FLC or LLC, which stand for first level cache or last level cache miss. In this case, the policies trigger recomputation upon the first level or the last level cache miss, respectively. The policy space is pretty rich. In the proof of concept design, we just played with these three types of policies, but any fancy prediction scheme actually fits into this picture. Now, to be able to recompute at runtime, as we covered before, we need to make the input operands of the leaves available. And the Amnesic Microarchitecture achieves this by allocating dedicated buffers. Dedicated buffers also help decoupling recomputation from actual computation, in other words, to protect the architectural state during recomputation. Next, I'm going to show you how these buffers look like. The first one is the history buffer, where the non-recomputable inputs, such as constants or program inputs corresponding to leaf instructions they go tagged with the leaf address into the history buffer. The next one is the scratch file. Communication during recomputation along the recomputation slice is established over the scratch file. In a recomputing slice, by construction, we cannot have any memory accesses, so all data flow happens over the scratch file. And to establish this, we need a renamer to have each register reference of a recomputing instruction mapped to the corresponding element of the scratch file. And fundamentally, the semantics of the renamer is not any different than the semantics of a classic renamer in an out-of-order machine. And finally, we have an optional structure, the instruction buffer, which can reduce the pressure on the instruction cache as recomputation takes place. Now, putting it all together, if the Amnesic Scheduler decides that recomputation is energy efficient, it sets a dedicated flag, the so-called recompute flag. If the recompute flag is reset, no recomputation takes place, and Amnesic execution becomes equivalent to classic execution. If recomputation is fired, namely the recomputation of a annotated load value is more energy efficient, this flag is set, and then execution jumps to the entry of the corresponding recomputation or recomputing slice. And we start executing the slice from the leaves. Each leaf first has to have its destination registers renamed. And following this, if its input operands are non-recomputable, it needs to probe the history buffer to collect the input operands. They directly go to execution units, and upon completion of execution, the leaf writes the corresponding result to the scratch file. Of course, we may have leaves which don't need any buffering, and in this case, we don't need to access the history file. So a leaf input operand, for instance, may be still residing in the register file, may correspond to a live register value in this case. We just need to differentiate between a leaf node and an intermediate node because their input operands come from different sources. In the case of an intermediate node, an intermediate instruction within the recomputing slice, all of the input operands come from the scratch file, and this is the only difference. The rest of the execution follows pretty much the same semantics. This brings me to the evaluation. We experimented with benchmarks from 4 different suites, and we looked into 32 benchmarks in total, but only 1/3 of them, only 11 of them, rendered energy efficiency gains higher than 10%. And we quantified energy efficiency in terms of energy delay product. The reason for that was twofold. The non-behaving benchmarks, so to say, were either very compute intensive and they didn't feature many energy-hungry loads, or actually, I should say, recomputation messed up with data locality. So it degraded data locality, and this was directly visible or was directly reflected to the energy efficiency. So in the following, I'm going to report the 11 benchmarks. We mimicked the Amnesic Compiler pass by a binary generator pin tool, and we implemented both the microarchitecture and scheduler using a microarchitectural simulator, namely a Sniper Sim. Let us first take a look at the energy delay product. On the y-axis, we have the EDP normalized to the EDP of classic execution, which excludes recomputation. For each benchmark on the x-axis, we have the corresponding profile under 4 different policies. Static is the runtime policy where no matter what, we trigger recomputation just blindly following the compiler hints. FLC triggers recomputation if the respective load misses in the first level cache, and LLC if in the last level cache. We also have an oracular policy which can, at runtime with 100% accuracy, determine where the corresponding load in the memory hierarchy would be serviced. So overall, we observe that Amnesic execution can reduce EDP by up to 87% and almost 25% on average. What did we observe generally? Generally, we observed that the static policy closely tracks the oracular policy. This means the probabilistic energy cost model of the static policy of the compiler was pretty accurate, and we achieved this accuracy by rigorous profiling. Actually, there is an exception, this SR benchmark, which under the static policy resulted in a negative EDP gain, and I'm going to talk about this briefly. But before then, when we look at the difference between static and FLC, it is mostly invisible, generally across all benchmarks, but LLC is the worst performer, and this is because of the overhead of probing the last level cache for each candidate load to be swapped by recomputation. Now, what is the stellar example for amnesic execution? An application which features many energy-hungry loads and at the same time where the corresponding recomputing slices are short. So the recomputation overhead proportionally wouldn't be excessive in this case. The 85% is coming from an application which exactly shows these characteristics, which is IS, and SR, where we see the negative gain, shows the exact opposite profile. So under SR particularly, the static policy, the compiler policy, was enforcing recomputation no matter what, but most of those data values were residing in L1. And at the same time, the corresponding recomputing slices were long. So they were so long that the overhead of recomputation couldn't be amortized. Let us next take a look at the length of recomputing slices. Here we have two histograms. On the x-axis, we have the number of instructions, recomputing slice features, and on the y-axis, the share among total number of recomputing slices within an application that features a specific number of instructions. Here we have two histograms just to show the two extremes. BFS is the application which featured the shortest recomputing slices and SX the longest. Over all benchmarks, we observed that almost 80% of the slices have less than 10 instructions. Actually, the share of slices that have more than 50 instructions was even less than 1%, and this is as expected because the compiler, which provides us with the hint, which provides us with the set of loads to be swapped by recomputing instructions, should be aware of diminishing returns. It cannot increase the length of recomputing slices indefinitely because with each increase comes an energy cost, and we are limited by the budget of the corresponding load to be swapped. So to summarize, amnesic execution makes the workload more compute-intensive to better utilize the classic machines of today, which are optimized for compute performance rather than communication. And by doing this, we observed significant energy efficiency gains. This basic implementation, the proof of concept design, actually forms the scope for our ASPLOS paper from this year, so I refer you for more details to the paper. But at the same time, this analysis was just the starting point. Amnesic execution, both at the microscopic scale and macroscopic scale of communication, enables many different optimizations. At the macroscopic scale, particularly, where the imbalance between communication and compute energy is even more pronounced, this would be the case, for instance, for sensor networks or IoT applications, we would expect a higher potential for amnesic execution. So before I conclude, I also want to acknowledge the hard work from our single student team. And now I'm ready to accept questions in case you have any. Thank you very much.